In this video, I'd like to talk more about geometric series, specifically by looking at a particular example problem where we're going to be adding an infinite geometric series. And I've written the sequence here so that we can see how we go from one term to the next. And what we can notice is that the common ratio here, the number that we're multiplying by to go from one term to the next, is 1/3. So this right here is what we call our common ratio. And to add up this infinite geometric series, we're going to need to use a bit of a trick. So we will call this sum here, this series, equal to s. You can call it whatever letter you want, but let's call it s here. And what we want to do is take our sum here and multiply it by this common ratio. So let's take this entire sum and multiply it by 1/3. And so essentially, we're going to distribute 1/3 to each of the terms here in this infinite sum. So when we take 1 and multiply it by 1/3, we just get 1/3. When we take 1/3 and multiply it by 1/3, we get 1/9. Then 1/9 times 1/3 is 1/27. 1/27 times 1/3 is 1/81. And this will go on forever. So the next term would be 1/81. You multiply that by 1/3 and you get 1/243. So the reason we want to do this is that now we can take our original sum, s, and subtract this new sum that we created by multiplying by the common ratio. So we're going to subtract 1/3 s. Now, this might seem a bit complicated because we're taking one infinite sum and subtracting another. But if you take it piece by piece, it is possible to do this. So for instance, in this original sum, we have this term 1, but we don't have a term that has a value of 1 in this bottom one. So we will have 1 when everything is subtracted off. Then we also have 1/3 up here, but we're subtracting this 1/3 down here. So 1/3 minus 1/3, that's just 0. Those will cancel out. And we have this term 1/9, and we'll be subtracting 1/9. So those will cancel out. 1/27 minus 1/27, those will also be 0. 1/81 minus 1/81, those will be 0. And you can imagine this goes on forever. The next one would be 1/243, and we would be subtracting 1/243. And so every term is going to cancel out when we subtract this yellow one from the pink one, except for 1 here. This will remain since there wasn't a like term in this yellow infinite geometric series. So we have an equation now. The original sum minus 1/3 of that sum is just equal to 1. And from this equation, we can actually solve for s. So from here, we could factor out an s from each of these terms. So we have s, and this would be left with a 1. This would be left with 1/3. And this is equal to 1. And 1 minus 1/3, so this is 3/3 minus 1/3. Well, that's 2/3. So s times 2/3 is equal to 1. And let me just make a bit more room here so we can finish this problem. So if we multiply each side by 3/2, the fractions on the left will cancel out since 3 times 2 is 6, and we'll be dividing by 3 times 2, which is also 6. 6 divided by 6 is 1. So you get that s is 1 times 3/2, or just 3/2. So when we add up this infinite sum, we find that it's simply equal to 1.5, or as a fraction, 3/2. So the conclusion is that we actually can add up an infinite amount of terms. And there will be a restriction on that. Namely, for this to be possible, the common ratio has to be a fraction. It can also be a negative fraction, but basically, the common ratio needs to be between -1 and 1, not including 1 and -1. And you can see that's true by just considering when the common ratio is not 1. Let's say we have 1 plus 3 plus 9 plus 27 plus 81. So now we have this geometric series where notice the common ratio, we're multiplying by 3 every time. So if our common ratio is bigger than 1, just think this through. That as we keep adding more and more terms, the number is going to get bigger and bigger, since we're adding bigger and bigger numbers every time. So this sum, we would say, diverges, or it approaches infinity as the amount of terms we add up approaches infinity. So there are some of these that we're not going to be able to get an actual answer for. But if our common ratio is a fraction, it is possible. And in the next couple of videos, we'll look at a couple more complicated geometric series where, again, that common ratio is a fraction.